In the last video we checked out some models and types and how centrifugal pumps, especially radial pumps, work. Now let's check out a little bit on the model. So the essential or basic points right here is, of course, you're going to have a work inlet, which is done by the shaft, which typically is either via mechanical or electrical energy. You will have one velocity inlet, one pressure at the inlet, and one height in the inlet. If we make the balance only on the pump, you can technically ignore the height. I don't think this is greater than maybe 50 centimeters. Compared to pressure and velocity, this will be almost zero. So we can ensure that if we are using the same velocities, let's say we have the same piping systems, then only pressure is what's going to change. It's very easy, or at least hopefully you see it very easily. You have this system. If you inlet have here work, and you have pressure going out and you have pressure going in, of course the only way out is if pressure increases. And this is the mathematical equation. It's heat flow minus work of the shaft minus work of the viscosity fluid or saw, which in this case will be 0, equals the mass flow, which is not shown here, but of course you know there must be some mass, the enthalpy at the inlet, the velocity to the square, the height times the gravity, plus, or actually this will be the change on second point. So I said before, if the height is very small, you can ignore this and this right here. And if the velocities are similar, or at least they are in the same, they have the same size of diameter, you can ignore it. So actually, if you're not using viscosity fluids and assume that there is no heat loss, you will have that the work of the shaft equals the change in enthalpy. So that's so easy. You will see later on when you apply real life scenarios, is essentially what's the enthalpy of the fluid going in, what's the enthalpy of the fluid going out, and you will be able to determine the work required for that pump. So here, once again, no heat generation. Actually, I will even take out heat flow. We can assume there is no heat flow going out. And no viscous work, and the mass going in and mass going out is the same, then you got this simplified. I will actually even increase saying that you can ignore the height of the system, because let's say you have 5 meters per second and 3 meters per second. When you do this difference and the enthalpy of the fluids, gravity times height is almost nothing, even 1 or 2%. So essentially, the work of the pump, which is almost the work of the shaft, is given by this equation. And if you want to get much more on the technical, this will be, I will say, more mechanical engineering stuff on what is the size, what are the angles, the design for the increase on pressure, what is the optimal degree and angle. And let's see what else we have for the volumetric flow rate. Well, you can do this as well. I'm not going to cover that, because actually what we are more interested is the balance right here. And if you are a mechanical engineer or interested on pieces and machines, you will be analyzing the impeller size, diameters, rotation, and so on.